So hello, thank you for having me. It's really good to come here and give a talk where I think I've attended many talks and definitely heard more than a few online. Um, the work that I'm presenting today is something that happened over the course of 8 weeks, past summer in 2018. It's part of this program called the NASA Frontier Development Lab. It happens on the West Coast at the Ames Research Facility. And what it is, in short, is they set up a room, throw about 30 people in that room, and close the doors for about 2 months. 15 of them are generally AI, machine learning experts. 15 of them are about domain knowledge experts in different fields. And NASA poses a set of challenging problems and asks us to come up with solutions if possible. So it's been going on for 3 years now. Last year was the third year. We're coming up on the 2019 session. I'll talk about that briefly towards the end. It's a really interesting place where you have both NASA funding it. It happens at the SETI organization, and there's private funding sources. For example, the Space Weather Challenge last year was funded by IBM, KX, with additional hardware support from other people. So it's a really interesting 2 months where we're asked to solve interesting problems. So you should definitely check it out. Before I start, I guess a quick show of hands. How many people here actively work on ionospheric scintillation, modeling that, predicting that sort of stuff? Okay.
Predicting?
Yep, exactly. And has anyone in the room looked into, or are they interested in applying machine learning? Have you been working on machine learning? Great. So the premise of the NASA FDO is to see if AI and machine learning can be leveraged to solve these challenging problems. That's the focus of it. It's growing as a field, as a technology. And as a society, we also have problems that need solutions immediately. So the idea is, can we fuse the two and come up with interesting solutions? So here's an overview of the talk today that I'm going to give. This is actually, I think 2 months ago, Andres from Surrey gave a talk about heliophysics and filling the gap about an STO instrument that went AWOL. So he was part of, so there were 2 space weather teams this year. One was his team, which was working on filling that EUV gap that happened because of the loss of that instrument. And then the other team, which was my team, we were working on predicting ionospheric scintillations. So the overview of the talk today, I'll be briefly talking about space weather and ionospheric scintillation. Then talking about a data-driven approach to the problem. What does that mean and what does that entail? Associated challenges with the process, and then some results. This would be like fairly interspersed. The results are in there with the mix along with the other slides. And what I want for people to take away from this talk is to get an idea of the challenges associated with machine learning and data-driven approaches. It seems like everyone's into it these days, and you can throw data at a problem at an algorithm, and then magically at the other end you have nice-looking pictures and results. But then behind that, you have 30 people struggling in a room for 2 months, trying to figure out how is it all going to work. So that's what I want you guys to take away from this talk. Not as much as what it is. When it means people said we applied machine learning to this problem. So here's a graphic that shows space weather and the current challenges associated with it. So I don't need to tell anyone in the room, I think, about this graphic too much. But we progress as a technological society, and we have increasingly more and more space assets, and these assets are being affected by space weather. And one of the main ones among them is GPS satellites. So we're putting GPS satellites out there, and then we're using GPS and GNSS as a service increasingly these days for multiple reasons. And when you have adverse space weather events, they can affect these GPS satellites, and then they can also affect the ionosphere, through which we communicate with these satellites. And so that's going to affect the system as a whole. So anything from navigation to precise agriculture, surveying of landscapes, civil projects, all these rely on the use of GPS and GNSS-enabled devices. So they're going to be adversely affected by space weather. There's been many estimates. Many governments have been interested in this problem as to how reliant are we on GPS as a service. And estimates have conservatively put a number on it, an economic number, which is at least $1 billion if we lost, say, GPS GNSS services for a day or 10 days. How much does it affect? And it's at least on the order of $1 billion per, I think, month that we don't have these services. And more increasingly, we're having more and more devices that use that can access the GNSS. So you have phones, dedicated GPS receivers, and all these things are going to get affected by space weather. So a quick overview on what it means for satellites to communicate with ground-based devices and how is that affected by space weather. So if you are using GPS to find where you are on the planet, then ideally you want 4 satellites, and by means of an extended form of triangulation, you can solve for where you are on the planet. But these signals propagate through the ionosphere, which is a charged medium. The signals that are used to talk between the device on the ground and the satellites is radio frequencies. So if you had ionospheric disturbances, then your ability to communicate with the satellite is going to get disturbed. So that is essentially what we call as ionospheric scintillation. When you have a disturbed medium through which radio signals propagate, then you can have the amplitude and the phase of the signal be affected. So you can either have amplitude fluctuations or phase fluctuations. And you have these small-scale structures called ionospheric bubbles, which cause the signal to get disrupted. As a result, on the ground, you have degraded performance of the GPS receiver, so you have increased uncertainty in your positioning or timing information. And in severe cases, you lose lock of the satellites altogether, so you can no longer communicate with the satellite. There's no signal coming through, and you're absolutely lost. So you have complete loss of positioning, and you don't know where you are. So that is not a situation that you want to be in. The goal then is to find out, can we predict the occurrence of these adverse space weather events, when they're going to happen, and if they're going to happen, take mitigative steps. The idea is, can we use a data-driven approach, given that we have more and more sensors, we have more and more ground-based receivers and satellites that can measure space weather effects. Can we predict the occurrence of adverse space weather events? So this is the scope of the problem. When we started working on this project at the FTO, we decided to focus on predicting scintillation, particularly at high latitudes, which is where the effects of space weather are most evident in some manners. It's also probably the most trickiest to model in terms of physics-based models. So can we predict scintillation at high latitudes? Further, when we say we're going to forecast scintillation, we're going to focus on one scintillation index, which is sigma phi. It's the phase scintillation index. The idea is to see if we can forecast on timescales ranging from 30 minutes into the future to 24 hours. So just like your weather forecast that you get on your phones, where you say, what's the weather going to be like tomorrow? Can we say, what's the space weather going to be like tomorrow? There's been an initial publication by McGranagan et al. Last year, which discusses techniques about the kind of data to use, the techniques to use, so the machine learning algorithms and the results associated with it. So we kind of use that as a reference point to get started. So can we use the results demonstrated in that paper and improve on them? And along the way, you have a vast variety of machine learning techniques that have been up and coming. So there's a certain set of tools that you need to figure out if they're right for the problem. So you can't apply all machine learning algorithms to all problems. You need to find out which tools are right for the problem and figure out what works best for the problem. So the talk wouldn't be complete if I didn't have a cartoon. And this is, generally speaking, the idea that people have from either side of the aisle when they talk about machine learning. So there's a guy, the so-called data scientist. He's going to be standing on top of a pile of data. And there's an onlooker who's curious about how machine learning works. And yeah, so what you take is you take all this data, you feed it into the machine learning algorithm, and on the other side, you just pick out the answers. And then, of course, the observer asks, what if the answers are wrong? You just keep stirring the data until the answers look right. So in some ways, machine learning is still a nascent science, especially in the context of applying it to problems that it wasn't originally envisioned for. So it's necessary for people who know machine learning and AI techniques to meet people who don't know it and who are domain experts, and for them to collaborate. It cannot be like a one-sided thing where you just give a child a hammer and say, here, do something. So when you start working on the problem, the first thing that you need to tackle prediction of scintillation is to figure out what kind of data sets are you going to use. In the case of predicting space weather and ionospheric scintillation, an easy guess to start off with is to find out what the sun is doing. So you have your usual suspects. You have fluxes from GOES, solar wind angles, the density and velocity. You can even use crude indices like F107 and KP and feed that to your algorithm. You don't know how well it's going to be, at the outset, you don't know how well it's going to be able to predict scintillation. You could guess that it's not going to do that well of a job because the indices are so crude, like on the order of days or hours, but scintillation happens on the order of minutes or hours. So you don't know how well it's going to do, but you can still include those indices. Then moving out away from the sun, you can start including other parameters, and more towards the Earth, you can start looking at magnetometer data. That wasn't something that had been done previously. So you go out and find networks of stations that are measuring the magnetic field strength on the Earth. And you use that as a potential data set. And then lastly, you want to find out what the state of the atmosphere itself is. That's one of your variables that go into the algorithm. So you figure out what the ionosphere essentially looks like. So we leverage data from the Chain Network, which is a Canadian network that measures the state of the ionosphere. And then they also provide parameters such as the phase scintillation index, the amplitude scintillation, and even the geospatial location of these receivers. You take all of that information, and they serve as model inputs. And at the other end of it, you want to predict what scintillation is going to happen. And that essentially becomes your model output. Any questions so far? Yes?
On the scope of the problem, can you, so this is, I don't really have a very good sense of this, but high latitude, mid latitude, low latitude,
yes.
Nature of this problem, which is most prevalent and also most impactful in terms of systems?
There's a really good graphic that I didn't include in this talk, but it's essentially at solar maximum, the occurrence of scintillation events versus latitude. And if you look at that, the scintillation predominantly occurs at low latitudes. So where the sun is just overhead, above, between the two tropics. So that's where scintillation occurs most. But it's fairly quiet in the mid latitude, so it doesn't scintillation doesn't happen that much in the mid latitudes. And again, there's a slight increase when you go towards the cusp region. When you talk about space weather affecting, so at low latitudes, scintillation occurs as a function of solar activity. So if there's a sunspot, if there's a high if there's a high level of solar activity, then you have scintillation events. But the small temporal fluctuations often manifest themselves at high latitudes. That doesn't happen as much at low latitudes. Does that help?
Okay, thanks.
So say sometimes I see on my GPS receiver,
Yep.
not receiver, what do you call that? The thing
Loss of lock.
yeah, the one you use in your car, the navigator.
Sure.
You can see 6 satellites.
Yes.
If you lose 3 of them, you can still have a pretty good. I mean, especially scintillation, I think of it as a relatively small scale thing.
Right.
You may lose, say, 3 of them, but you can still get a pretty good reading, right? Is that the case, or it's already if you lose 3 of them, you're totally messed up?
So for starts, it has to be 4.
Oh, okay.
But you're right. Often case, what happens is they use solutions from multiple combinations of satellites to improve your precision. So more satellites doesn't hurt. It just improves your solution. But you're right. You can, as long as you have more than the minimum number of satellites, you can still have a reliable solution. The issue is, so say 3 of your 7 got knocked out and you still have a solution. Those 3 are still going to be serving other receivers in other locations. So the question is, are they affecting those receivers in another area? But you're right. Okay. Yeah, so the first step, as soon as you start gathering all this data, is this process that we call data wrangling, which is essentially going into these data sets, figuring out what's contained in them, and then making sure that they're in a format that can be fed into a algorithm. I'll be giving some examples of this as we go along, but for starts, here's phase scintillation index data from these stations. So the name of the stations, the short form is along the right, and this is for 2015. So you start looking at the data, and we started, I think we were looking for data from 2013 onwards, which is when we had like a consistent database for all the data sets that we're looking at. But then you have, they're ground-based instruments measuring physical quantities. So it's not necessary that they're operating all the time in full capacity. So you have obvious data dropouts, which you can see in orange. And then for the most of the time, you get good data. But then in other years, you have issues. This is from 2017 for the same set of stations. You have issues like biasing issues at the receiver, due to which your phase scintillation index gets kind of knocked out of whack, and it doesn't make sense. So you need to make sure when you start this process to gather all the data that you think is useful for it, and actually look at the data itself. It's extremely important to account for unavailable data, data dropouts, and other noise that might exist in your data that you might not think of otherwise. So what we did after gathering all the data is start pre-processing it, which means we started generating the so-called super observations. So if you had a single receiver and overhead it's all multiple satellites, then there's a phase scintillation index associated with each of those satellites. Now, the observations occur at a certain elevation angle at each receiver. So what you do is you project each phase scintillation index to the vertical, and you take the median of them. That's what a super observation means. You also start eliminating points where the satellite lock time is less than 200 seconds, just to eliminate noise from your data. You also begin to apply elevation masks. So you consider any satellite which is fairly low in elevation to be a bad data point, because it may result in multipath effects. So a satellite sending a signal to the receiver may get to that receiver if it's at a low elevation angle from multiple paths, and that might look like scintillation when it actually isn't. So you apply these elevation masks. And then you generally account for bad data points, nans in the data, missing data, negative values that aren't supposed to be there but somehow snuck in. And then interpolating and decimating data. So if you had magnetometers, for example, they often end up putting out data at 1 hertz, so a data point every second. But then you have GPS receivers that might put data out only once every minute. So kind of making the entire data set uniform on a time grid so that you can use it. And this is an example of that. So this is over one station, over the course of one day, what all the satellite passes look like, and then you simply apply an elevation mask to get rid of anything that's less than 30 degrees in elevation, and then you use that as your input data set. Similarly, this is for one station. We create this super observation. So take the sigma phi and then project it to the vertical and take the median. So that's what it looks like for over the course of a day. The other thing that you can do once you get all of this data that you want to use is something that we call feature engineering. And what it means is using the best or applying the data that you have in the best manner possible. So the raw data in itself might not be in a readily usable format. So you take the data and you apply a transform to it that makes it more usable by the algorithm. Examples of this include taking an input data set and time shifting it. So instead of using the data as is, you delay it or advance it by a certain amount, usually delay it. You can take the trigonometric transforms of certain of parameters like local time and day of year. So if you had, so scintillation depends on the sun. So at low latitudes, for example, you have diurnal effects. So if you took the trigonometric transform, then you can account for those cyclical effects. And then you can also have time integrated values. So a window over which you integrate a physical quantity and use that as an input. And examples of this are tech, the rate of change of tech, and then the magnetic field strength. So you can produce these additional features that exist in your data, but then they're not readily available to the algorithm, and you use that as inputs for your machine learning process. So when you whittle down, so at the outset, we started off with this huge database of all these missions, all these receivers across the globe. But then once you start whittling down like availability in terms of time, location, the fidelity of the data, you quickly start realizing that there's not that many data points that you can use effectively. So what we ended up with is a small number of stations in Canada and at high latitudes. This is from the chain network. And we were looking at receivers of only one type so that there's no biasing issues. And we're also hoping to find co-located magnetometer stations. So Charisma is a magnetometer station, again, Canadian-based. And we were looking for co-located ionospheric measurements and magnetometer measurements. So there's about 4 of those, but we still used, I think there's 10 stations here that we still ended up using the data from all of those stations for the study. And this is kind of what it looks like at the start. So you have a data set that you create with all these input features. So starting with the solar wind parameters, you have tech, we have F10.7 here, you have the S4 scintillation index, and then all the way to sigma phi projected to the vertical. And then you also have these engineered features. And this is what a typical data frame looks like. So it's essentially a huge table of all the data that you found was good. And it's essentially a time series. So this is time stepping at 1 minute. And this is, so this table is a sample of for one station. So given the number of stations, we were looking at data from 2015 to 2017, so 3 years worth of data for at least 10 stations at 1 minute cadence for 24 hours each day. So that data ends up adding up really fast, and you end up with like a huge data set. So now you essentially mix all the ingredients and then cross your fingers and hope something nice happens. But wait, what do you even mean when you say forecasting scintillation? Like we never define the problem as to what scintillation is. Like we agree that scintillation means loss of signal, but in terms of telling a algorithm to predict it, what do you mean when you say forecast scintillation? Essentially, what do you want the machine to do? This is a point at which all the participants in my team, we kind of sat down and struggled with. It seems like a fairly basic question, but asking this question dictates how you're going to proceed from it. So you have this data set and you want to predict scintillation, but then do you simply want to say scintillation's happening, yes, or it's not happening? Or do you want a measure of the scintillation index itself, so the strength of the scintillation? So that's a question that you have to ask because it dictates what your step forward is. There's many different approaches in terms of machine learning, in terms of algorithms. So there's an algorithm which can essentially act as a classifier. So it'll just tell you if scintillation is happening or not. But then there's other methods which would tell you or try to predict using, say, regression, what the strength of the scintillation is. So the first cut that we did, which followed the paper that I referenced at the start, which was McGratting et al. And he's done work regarding these support vector machines. So it's a type of machine learning algorithm which acts as a classifier. So given all this data, given scintillation indices, at the end of the day, it's going to tell you here scintillation's happening or no, scintillation's not happening. Even for that case, you need to define what's generally known as a decision boundary. And in our case, we define the decision boundary as a sigma phi value of greater than 0.1. We're going to say that defines scintillation occurring. And anything less than that, we're going to say the ionosphere is fine. There's no scintillation happening. And what support vector machines do essentially is if you had a large number of data points and you want to classify certain points. So in this example, they're classified by color where you have red balls and blue balls. And you want to come up with this decision boundary which separates the two. In this space, the definition of this boundary may be nonlinear and not that straightforward. But there's techniques by which you can transform these input data features into a space where you can define a simple boundary. So in this case, it's a simple plane that separates the two colors. So this technique can be extended to multiple dimensions. So what that means is when you have multiple input features, so the large number of input features that we have, you can make a transformation such that you can easily define this boundary. And then once you have this boundary defined, you can switch back and forth between the two spaces, and you don't really have to worry about defining your decision boundary in this space. So we started developing SVMs as our first machine learning algorithm to predict scintillation. And once you start throwing data at it, the first question that you want to ask is, well, how well is it doing? How well is it performing in terms of learning and predicting scintillation? And there's many metrics to do that. Here's this matrix, also known as a confusion matrix, is essentially on the left you have true labels. So given a data point, is scintillation happening at the data point, yes or no? So there is scintillation, there's no scintillation. And then on the other axis, you have what my algorithm is predicting. So again, the algorithm predicts no scintillation, and then the algorithm predicts scintillation. And then you have the combination. So you have what you want is high true negatives and high true positives, and fairly low false negatives and false positives. questions so far? Okay. And here's another nice visualization of the same idea, which is the circle, anything inside the circle indicates predictions by the algorithm. On the left, you have all the true occurrence of an event, and on the right, you have all the true negatives of the event. And effectively, ideally speaking, you would want only true positives and true negatives. You wouldn't want false positives, and you wouldn't want false negatives. So each of these events you can classify and come up with metrics known as precision and recall. They make sense if you sit with it for a few minutes, but combining all of this, you can come up with something known as a true skill score, which is a metric that was established a few years ago now. And what the TSS states is it's a metric which says it's going to range from -1 to 1, where 1 indicates at any given point of time your prediction is dead on. So it's getting the true positives and the true negatives right, and it's not doing any false positives or false negatives. So a correct classification is 1, completely incorrect classification is -1, and then if you have a TSS of 0, then it means it's chance. It's the flip of a coin. So ideally speaking, you want your total skill score to be as close to 1 as possible, which indicates it's making good predictions. So once we started putting the data and the algorithms together for each SVM, so we had SVMs defined for the data set as a whole, and then we also had SVMs defined at each geographical location for each station. Given the entirety of the data set, we choose 50,000 points in random. We train the model to learn from 40,000 points, and then we keep 10,000 points aside, which the model doesn't see, and then we test, once we've trained the model, we test it on those 10,000 points and see if, and we see how good the model does. Another thing to account for when you do this training is something called class imbalance. So if you look at the data set as a whole, the number of scintillation events that happen in the data is only about 3%. So the occurrence of scintillation in itself is a really small percentage of the total number of data points available. So that's something that you need to account for when you do this training, because it's really easy for the algorithm to just assume that most of the time there's no scintillation happening. So I'm going to consistently predict scintillation's not happening. So this is some results that we got from one station, Fort McMurray. Again, this is here for reference, and then this is the result itself. So we have fairly high values of true negative and true positive results, and it's a small effect on the false negatives and the false positives. But once you have it for one station, you can begin extending it for other stations. So what we did was so that was a 30 minutes into the future prediction, and what we did was we started running the SVMs for all stations. So we developed an SVM for the entirety of the data set, but then we also developed SVMs for each individual station. The McGranigan et al. Paper from last year, they defined one SVM for the entirety of the data set, and this is total skill score as a function of time. So how long into the future can you make these predictions, and how good are they? So we that first row is where we started off, and as you expect, so you have a total skill score, and then over time that skill score degrades, so it doesn't perform as well. But then curiously enough, we found out that instead of taking the data set as a whole, if you started taking individual stations and built SVMs for individual stations, you can do much better. And that's what you almost consistently see. There is, however, an aside here. So while generally speaking, stations seem to do better when you have individual models for each of them, There's a few exceptions. So these three stations, for some reason, despite the fact that we built models dedicated to them, perform worse than the case of a model developed on the whole data set. And that was interesting, and it was something that we discovered towards the end of the program almost, and we're trying to figure out why that happened. And so if you step back from machine learning and all the data wrangling, and if you go back and you look at the map of the stations geographically, you see that curiously enough, they're located close to each other. We didn't chase it down all the way. We didn't quite figure out what these three stations had in them that caused this to happen. But it's worth noting that despite all the algorithms and processing power that you might have, it's still always useful to like step back away from ML and AI and like just look at a map and see what's happening. Another thing that we kind of tested almost as a sanity check, but out of curiosity as well, is once you developed, say, a SVM for one station like McMurray, can we take that SVM and test it on data coming from other stations? So this is on the x-axis you have stations, and on the y-axis you have total skill score. And what we did was we used the SVM that we trained on data from one station, and we applied it to other stations. And consistently, you almost see that the predictions are worse off. So what this indicates is that the algorithms somehow are location dependent. So there's, yes?
Say something about the three stations that you have.
Yes.
They are all on the coast. Perhaps the ocean tide models are not correct for that, or that's the only thing that I can think of.
Yeah, it's not something that we followed all the way through. It's something that we were sitting around one afternoon and we're like, hey, that looks funny. Why does it look like that? And then we couldn't figure it out. And then we pretty much pulled up the map to see where the stations are, and that's what happened. You're right. It's very much possible that might be the case.
Station displacement is mostly affected by that on the coast.
On the coast. Yeah.
Do you de-weight those data points in your combination?
How do you mean de-weight?
When you do the SVM for all stations, because of the few stations that are bad,
right?
It does actually affect your entire solution when you have bad data in there. So if you de-weight stations,
so reduce the weight of these three stations? No, we didn't, because we didn't want to introduce biases of our own into it in some ways.
I don't think you would introduce biases, but it's just my thought.
Yeah, no, that's a good point. A decent amount of what we did was we're going to throw the data at an algorithm and see what the algorithm does. That was it was a fairly brute force approach in some ways that needs to be improved upon. Any other questions? Yes?
Actually, I was thinking that I'm not sure in your initial data you provided, does it have information on, say, for example, tide or other lower atmosphere information? If not, how will that affect? Because that seems that that's not a training criteria for your.
Right. So among the input features, there was latitude and longitude information, which we thought would be useful if you're making, say, time series predictions. So scintillation happening here, is that going to propagate eastwards or westwards in longitude? And we were hoping the algorithms might infer that, but there wasn't any information about the state of the atmosphere in itself. There was tech values that we included, but we didn't include if the station was near the coast or those kind of disturbances. Yes?
Ionosphere has its own memory. When you do the model training, do you take into account the historical solar wind and the geomagnetic indexes to train the model?
Yep, that's an excellent question. So when I mentioned feature engineering, when you provide these integrated values, that is something that accounts for the the memory of the ionosphere, so to speak. So I think I have a slide coming up, which what we did was, once you have all these input features, we did a principal component analysis and had the algorithm tell us which features are important and which are not. And some of that historical information we were told was important. But yes, we did include historical information in the sense that we integrated values of physical quantities over different timescales and used that as input.
Thank you.
Does that make sense? Okay. Yeah. So once we had a good handle on creating and running these SVMs, we did some more data wrangling, and that was this principal component analysis. So we had the algorithms tell us which input components had a significant effect on the predictions. And what came out of that was, to a large degree, the rate of change of tech, integrated over 15 minutes, the X component of the magnetic field measured, so magnetometer data measured at the ground, those were found to be important by the algorithm. So it's now the algorithm turning around and telling you that, hey, these are the most important input features that go into predicting scintillation. So this provides a certain amount of physical intuition about the problem and what features you should be looking at, instead of just giving it all the data it can. And what this really helps out with is speeding up the computation. Instead of having hundreds of input features, we can just select the top 20 and reduce the computation time by like order of magnitude. Once we had a good handle on SVMs, we got ambitious and we started the more cool stuff. And neural networks, or MLPs, multi-layer perceptrons, is something that we wanted to try out. There's many libraries dedicated to it, which make it really easy for you to set this up and have it running. And Andres might have spoken about it when he gave his talk, but you have what these comprise of is primarily an input layer where your data is fed in, and then you can have one or more layers of hidden layers of neurons, and what each of these neurons is, in effect, the neuron itself produces a linear combination, and beyond that, the outputs are taken and they're fed to a nonlinear function, and you can have multiple layers of these. And at this step, what we decided to do was, instead of treating the problem as a classification problem, where you have sigma phi below 0.1 is non-scintillation and above is scintillation, we decided to ask, can we actually predict values of sigma phi? So coming up with, so treating it as a regression problem and see if we can predict the sigma phi values themselves. So we had some preliminary results right at the end of the program, where for a time series, we can predict scintillation fairly well. So in blue, you have the true values. In red, you have the predicted values, and the model seemed to do fairly well. It was predicting scintillation a decent amount. The issues became when you have really strong scintillation events. The model wasn't doing as well. It wasn't quite getting there. That's one issue with the model, and then the other issue is, once you generate these kind of results, how do you compare it with what already exists? How do you know if it's if it's predicting accurately or not? So there's ways of taking the output from these kind of neural networks and then kind of feeding it into a classifier again, and then treating it as a classification problem again. Yes?
How many hours ahead of your position here?
This was, I think, a 30-minute in advance calculation. I'll have to go back and check what the exact...
It's only predicting 30 minutes ahead.
I have to go back and double check that number.
It might be predicted in the sense of using all the model, all the input information available, regardless of time lag. I mean, right? There is that sense of prediction, meaning not forecasting, but simply model fidelity. Is that what this?
So when you make these predictions, you test the model against data it hasn't seen. So it's working on a set of data that hasn't been given to it beforehand.
Right, but I mean the input values. I'm just wondering if there's any time lag in the availability of input data in this plot.
So
Because the timing of all these events looks excellent.
right. So when you ask it to make predictions, you're no longer giving it the inputs as well. So those are held back. So when you ask it to make predictions, you give it the input features and then ask it to produce a sigma phi index value. So that can be at any.
You must give it some. I mean, you're giving it the solar wind or IMF or some other index, right?
Right.
F10.7.
Right.
And the question is, how far ahead is the prediction being made? Because I can certainly believe that if it's dominated by upstream solar wind data, that you could get a half-hour fidelity. Let's see, what's the time scale there? It's 20.
It's just in
It's
minutes.
Time in minutes.
Yeah. Yeah, I'll have to get back to you on.
So maybe the time
Exactly
isn't
what
as
the-
exact as it looks. But
Yeah, the question is, you can say, just nowcasting or forecasting.
Right.
Forecasting how far ahead you
Into the
forecast.
future.
I'm wondering if this is a nowcast or a forecast, basically.
Yeah, he said he doesn't know.
Yeah, I'll have to get back to you on that one.
He doesn't know how many minutes.
But at most, it's like half an hour or something.
Yep.
Because
No, I think the form you showed earlier does show the scores, the scale score dependence on time.
Yes.
30 minutes
Right,
or
right.
an hour. So it does. I mean,
So in that case, we did have a time dependence prediction. It's just that in this case, I don't quite remember what the forecasting duration was. So in that case, yeah, we did have going from 30 minutes to 24 hours. Yes.
So the plot that you have, is that the test data set in 2017? Am I understanding?
Yeah, so we trained on the years of 2015 and 2016, and then we tested on the entirety of 2017.
Is that what it's showing, or
Yes.
so it has nothing to do with the prediction, how far it predicts in ahead of time, like 30? Is it so?
So, yeah,
It's
so,
just related to what they're saying.
yep.
So I'm just wondering if this is actually the test data that you're showing, not really actually the prediction. I mean, what they're saying, like forecasting or nowcasting, it's just the test data set that you're using right now. Is it related?
So it is showing predictions on the data inputs from 2017, yes. So it is just the test data set.
And this is for all the stations?
This is for all the stations, yep. So it's a combined model that was made from, input data from all the stations.
How's the station, how's the performance when you use one station that has the best score?
So how do you define in that case?
You said you use all the stations to do this test. So if you use one station, can you create the same?
No, actually, I'll take that back. So this one was done on the Fort McMurray dataset. So the MCM station. So yep, this was trained and validated on data from MCM, and then tested against just data from that station. It wasn't done on all the stations. Yeah. So that kind of that's where we kind of left the work off. There's still we're still working in some ways to kind of improve on this and see where we can take it. But a lot of what we learned from the work that we did over the summer was instead of defining one SVM for the entire data set or one algorithm or model for the entire data set, despite space weather being like a global phenomena, the model can still suss out localized features. So the model performance improves when you account for the locality of the data set. Instead of defining one model for one SVM or one neural network for the whole data set, account for data from each station and then apply the data on that. That seems to generate better results. The predictions also seem to be aided significantly by including the magnetometer data. And yeah, one thing that we definitely learned was before you apply any kind of technique, it's always useful to step back and visualize the data and understand what it is that you're giving the algorithm to begin with. It's not a cure-all, it's not a solve-all. You still need people with domain knowledge to tackle this problem. Just for a few minutes, the FTO program, it's a 8-week AI accelerator. Registrations for this year are open, and they're in fact asking for people to pitch in with ideas about challenges that they think are important that need to be tackled, that can be tackled by this. There's a workshop happening in California on the 29th of this month. If you go online, you can find it fairly easily. And it's a really interesting place where people come together and find interesting solutions to problems. So, and this is just some photos from that 2 months. A lot of it is heads down coding, and then some of it is having fun on the side. But it's a good 2-month program where everyone learns a lot. Thank you.
We've had quite a bit of discussion already, but we do have time for a couple of questions.
Have you tried other machine learning techniques besides SVM?
No, we were looking at doing LSTMs and RNNs to account for there's some time history data. We went down the route of implementing LSTMs, but we quickly backed off from it. The reason why we backed up from LSTMs is we found out we could implement recurring neural networks with similar performance as LSTMs without the same amount of complexity. So we decided to pursue RNNs, and then we ran out of time. Yes?
So in one sense, this machine learning approach is an engineering solution to a physics problem, science problem. But what comes out of it, for example, in your conclusion slide, the fact that the magnetometer data improves the prediction, and that kind of poses the question, it's not obvious at all why magnetometer data has anything to do with scintillations. And so are you kind of working backwards and asking, so why is that? What is it about the magnetometer or the magnetic measurements that is improving the prediction of scintillations?
Are we asking that question? No. In the sense that at high latitudes, we almost expect in some ways space weather to be reflected in magnetometer data.
So it's the fact that there's a driver that's affecting both, but there's not a causal relation necessarily between scintillations and magnetometers.
Right, it's the aurora. I mean, it's the mighty magnetosphere, right?
Yeah, but scintillation phenomena is the small scale stuff.
At high latitude, they accompany aurora light.
And magnetometer measurements are measuring large scale responses.
Yeah, but when there's an auroral event, and the oval expands and comes down to lower latitudes and encounters magnetometer stations is measurable, we say, oh look, space weather. And at the same time, you're getting ionization and precipitation and small scale effects in the ionosphere that are causing scintillation. So yes, C and B are both caused by A. M, that is, in your case. Right? I mean, that much we understand about the phenomenon.
Yes, but then there's still some amount of locality even to magnetometer measurements. It doesn't reflect the magnetic
Right. That's
fluctuations.
why they do better than, say, KP.
Right.
Sure. Well, I mean, a station will
Yes.
do better than KP in
Right.
terms of correlations, right?
Yeah, I mean, that's what we used to do in astronomy. Sit inside where it's nice and warm, and then the magnetometer starts going. You go, everybody puts on their parties, it's running outside, and then you come back inside, and they say, the scintillation thing was going nuts. All happens at once. But your principal component analysis hopefully gives you some insight into
The physics of the
maybe gives you some insight into what's important and what correlates, what maybe even anticipates. And as far as that anticipation part of it goes, I'm still unclear. This distinction between forecast and prediction, right? I mean, if the magnetometer measurement at this instant must give you a lot of knowledge about whether or not scintillations are happening.
Right.
But did the magnetometer measurement from an hour ago really do you any good? That's the part I'm a little confused about here.
So at the end of the day, it boils down back to the sun. So in effect, you're asking what's the sun going to be doing in an hour or in 24 hours?
Right, and it's hard to be, a magnetometer may not know that too well.
Right, or your whole data set for that matter might not.
Base data knows.
How far into the future?
Half an hour?
Right. So the goal or the hope is that we can predict space weather on much larger timescales. So you want to ask, is it going to be? Are we going to have like a solar storm tomorrow? What's the index going to be like? Is it going to be? Am I going to have scintillation at 5 p.m.? If you're working towards that, then you want to find out what the sun's doing on those kind of timescales, which you don't know if the atmosphere has any memory of, like, can you infer those kind of information from given a large enough data set?
Well, to pursue the meteorological example, you can't, it's difficult to forecast the weather without knowing that larger scale, big picture of what's coming in from the west or whatever.
Right.
But if it's raining now, it vastly increases the odds that it'll be raining when we go home.
Yes.
Right? So that always helps. And space weather isn't that different. The big storms last for a while. Everybody knows that.
Right.
So in that sense, there is predictive capacity to resulting measurements. Measurements of what's going on in the ionosphere
Right.
at this instant.
Yes.
So, look like the skill score, the best one is 0.68. So it's like, is that higher than that?
Slightly better than that. I think it was.
I just want
I want to say we did slightly better than that.
There were some in the
Okay,
7s.
6, 7. Okay. So does that mean that's if you're using different algorithm, is it maybe it's improved slightly? But is this fundamentally, the limitation of AI or whatever the machine learning skill, because you cannot just capture all the physics by those mechanical process behind that.
So
Is that fundamentally, that's as best as you can do in terms of predicting space weather.
that's a really good question. So if you look at neural networks, the way people tend to sell it is it's a set of neurons or a system that can reproduce an arbitrarily complex mathematical function. So if physics is, at the end of the day, a set of mathematical equations, and neural networks can reproduce arbitrarily complex functions, then the only limitation is data, having enough data. But no, that's not a proof by any stretch of the imagination.
From your experience, do you see other field that is doing better using this kind of machine learning? Much better skill scores.
I can maybe speak to that because
Sure.
I've seen people replace very expensive interpretation techniques for spectropolarimetric solar data by neural networks that complete in milliseconds, and basically they get exactly the same results. So, I mean, if you were to calculate this kind of a measure for those, you'd get 0.99999 or something like that. It would be very close to
That's
one.
a straight mathematical problem, really.
No. It's that's fairly complex stuff. You're synthesizing radiation out of a model atmosphere. So normally you would attack this kind of problem with a forward model, where you modify your atmosphere and synthesize radiation, try again because it doesn't fit, and so on and so forth until you get a hit. And the neural network just looks at the profile and says, "Oh, it's this," and gets basically the same result. So, speaking from that, I think you can expect a neural network to do much better than this if you have the right data. So I don't think that
the same data.
I don't think that these scores are a limitation of what a neural network or an AI kind of solution can do in principle. Like, you can do better than this. Maybe not for this problem, but certainly for other problems.
Well, maybe if all the parameters and output is a linear relation, then probably you can do much better. But in terms of system, atmosphere, ionosphere, it's intrinsically nonlinear. Therefore, you probably very hard to get it much better.
So are these spectropolarimetric interpretations. So yeah.
Well, but if you weren't asking the question, can I reproduce my spectropolarimetric measurement, instead ask the question, what is the actual magnetic field inside of the sun? You might not get its highest skill score.
Yeah.
And that's what, in some sense, he's asking here. He's comparing all these diverse measurements to something that somehow results from all of that chaos up there.
Right.
And because it's inherently a turbulent process, it makes it particularly
Hard to.
intractable, or maybe more tractable to this kind of approach.
But I would argue that the question, what is the magnetic field in the solar atmosphere, is of the same kind of difficulty as the question that's being asked here. Yeah.
But you don't really know that. You just say it's the same answer from these two different methods.
But so my point is that if you had a method that did this perfectly, you could get an AI that does this perfectly too. All right, I think we should end the discussion here, but Karthik is going to be here.
Yeah.
I assume he doesn't have to catch a flight to get back home.
Nice.
So if you want to continue the discussion further, then please go ahead.
Okay.